All right, so today we are going to be working through chapter 9. And we're going to start off with some nomenclature, just like we did yesterday. So yesterday we talked about alkenes. Today we're going to be talking about alkynes. And similar to the way that when we talk about, so this 3-carbon chain would be propane. It's an alkane. It ends in A and E. If we add a double bond, this is now a propene. And then lastly, or like as we're doing today, if we have a triple bond, this is going to be a propyne. So it's an alkyne. It's going to have this suffix of y at the end of our naming. All right, so a couple things to note is that alkynes are linear. So because of that, they look a little bit different. Especially when you have one that is something like butane. So this structure here sometimes confuses people. Really what this would be is CH3 carbon, triple bond, carbon, CH3 here. So just getting used to the fact that this is a linear chain. It's not going to have any sort of like, it's never going to be this. That's an improper way to draw one of these because it is 180 degrees away from the other center. Okay, so let's talk about some naming for these. So very similar to alkynes. A little easier, honestly, because we don't have to determine E or Z for them. So if I have one that looks like let's just do the non-chiral version of this first. This here, the way that our priority naming is going to work for an alkyne is that we're always going to go through the alkyne with the lowest number we can. So for this structure here, there's 2 different possible longest chains. You can either go right to left, 1, 2, 3, 4, 5, 6, or left to right, 1, 2, 3, 4, 5, 6 here. Because our alkyne starts on 2 versus 5, the right to left is going to be favored in this case. I lost my 4. I'm going to write these out down here just to get them a little bit closer. So similar to with an alkene here, we're indicating where it starts. So this would be a 2 hexyne. And then from here, everything else is the same as we have been doing. So on 4, we've got a methyl. 4, we also have a chloro. 5, we have a chloro. This would be C comes before M, so 4, 5, dichloro, 4 methyl, 2 hexyne. And like with a double bond, you could also write this as hex 2-ine. Either way is fine. When we do, so we're going to do one that has both a double bond and a triple bond in a second. And that's going to have a specific way that we're going to name the end of this. But when you just have one, it doesn't matter which way you go. All right, any questions up to this point? Okay. So, in terms of priorities, for how you're going to be numbering things, let's break this down a little bit. One, two, three, four, five, six, 7. At this point, our highest priority group is going to be an alkyne. Our second highest would be an alkene. And then from here, it's just normal like methyls and halogens. So for something like this here, where we have 2 different numbering options, 1, 2, 3, 4, 5, nope, 6, 7, versus 1, 2, 3, 4, 5, 6, 7 here. Our alkyne is going to be our highest priority group, which means that we're going to go through the alkyne before we go through the alkene. That will trump it. So for this here, we are going to be using the blue pathway. So basically at this point, alkyne is at the top of the pyramid. All right, from here, we need to determine E and Z because we have a double bond. This is, oh, wrong button. If I cut it down the middle, between H and methyl, methyl's higher priority. Between H and methyl, or H and, I don't know, butyl here, highest priority. They're on opposite sides. They're in like a trans configuration, so this would be an E double bond. So to name this molecule here, our double bond starts at 5, so this would be a 5E. We have 7 carbons, which makes it a heptyne. When you have both a double bond and a triple bond, you're going to put the double bond first. So you would name this as a hept. You would indicate where your double bond is. 5-ene. And then you're going to indicate where your single bond or your triple bond is. So 1-ine. And that's also kind of an alphabetical thing. So E and E comes before Y and E. So we're going to use that one first.
Can we write 5-heptane instead?
Yeah, 5 heptene 1 ine would also be fine, yeah. You just you can't write it as 1 heptine 5 ene. This would be an improper form. So this is also fine. Just make sure you're putting them in alphabetical order. Okay, I'm going to draw up a molecule and give you guys a couple minutes to try to work through it and see if you guys can name it, and then we will go through it together. Okay, I'm going to give you guys, let's say, till about 9:33 to try to work through this one, and then we will give it a shot together. All right, so we're going to want to count. So we go through our alkyne first. So we're going to be going right to left. So 1, 2, 3, 4, 5, 6, 7, 8. Should be an octyne. We also have a triple bond or a double bond on 3, so it gets an oct. 3-ene. 1-ine. We had a methyl group on 4. We have a bromo on 7. Our bromo needs to determine its chirality. So BR is our highest priority. Followed by the left part of the chain. And the right here, this is going counterclockwise. This should be S. Taking a look at our double bond, cutting it in half. The alkyne would be a higher priority than the hydrogen here. And then the bottom would be a higher priority than this methyl group. So both our higher priorities are on the same side, making this like a cis configuration, which is Z. So putting this all together, our double bond is on 3, so it's a 3Z. Our BR is on 7, so it's a 7S. We would have parentheses 3Z, 7S, alphabetical order. B comes before M, so 7 bromo. 4 methyl. Oct, 3-ene. 1-ine. Someone in the chat asked if you could write 7S, 3Z, and I mean, you're supposed to put them, you need to put them in numerical order, so it really needs to be 3 and then 7. So kind of like you're doing alphabetical here. These need to be in numerical order here. Do the bond names always go together at the end like that, regardless of alphabetical?
So like, see how like oct or like octene, ine
Yeah.
at the end and it's together. So if we were to have like hexene, would that go before methyl?
Oh, sorry. Yeah, your longest chain is always at the very end.
Okay, thank you.
Yep. All right. Any more naming questions before we start on some reactions for the day? All right. So we are going to move into some preparation of alkynes. Nope, wrong spell. These are pretty straightforward. So if you think of your normal preparation of an alkene, we would start with some sort of haloalkane, adding in a strong base. We can do an E2, pull off a proton. To make an alkene here. To make an alkyne, we're just going to do this twice. So there's a couple of different options. So your first option is we have both the BRs in the same center. We add in sodium hydride here. We're initially going to pull off one of these. And then from here, these two hydrogens are actually our most acidic positions. So from here, you can just pull off another one of these. If you add more base, it'll automatically go to one of these two. It doesn't need to be anti like it does for a normal E2 because they're going to be perfectly aligned either way. So you can do a syn elimination or an anti elimination to make an alkyne, like so. So you could also just write this as excess NaH will get you to your alkyne here. The other option is you can have them next to each other. So if they are adjacent and you throw in a strong base, so we keep using NaH. This is a small base. You're going to selectively want to pull off this more substituted secondary proton. And then same as before, your double bond protons are more acidic. And this will lead to a triple bond. So whether you have them staggered or right on top of each other, both of these have the ability to form triple bonds. Axis. All right, so once you have a triple bond, you can reduce it. So much like a alkene here, if we throw in H2 and platinum, this is going to reduce our double bond to a triple bond. And as we talked about, if we have a bunch of these, because H2 is a gas, you really can't control it. It's going to reduce everything down to just single bonds here. When we deal with triple bonds, it's going to do the same thing. So Throw in this butane here with H2. This could just fully reduce this down to an alkene. It's not going to stop at the it's going to reduce it all the way down to the alkane. It's not going to stop it at an alkene. And if we had a combination of the two, we're out of space. Throwing in H2 is going to reduce absolutely everything. 1, 2, 3, 4, 1, 2, 3. And you just get a giant straight chain alkane. All right, so if I want to get a double bond out of a triple bond, I'm going to use what's called a poison catalyst. So the poison catalyst we use in this class is what's called Lindlar's catalyst. And what this will do is typically the way that this reduction works, if you remember, when we add H2 across a bond, it's going to add in a syn fashion. So we would temporarily get this, but because there's so much H2 in solution, it's going to immediately just take us 4-carbon chain here. So if we add in a poison catalyst, we're able to stop it at this point here. So as I mentioned, our poison catalyst is to be called Lindlar's catalyst. So to do this reaction, you're going to add an H2 and Lindlar's. Is that right catalyst? It just says poison. Oh yeah, it doesn't say catalyst. And when we do this, this is going to let us create this double bond here. In order to get our trans configuration, we're going to do something very different. So for a trans configuration, what we're going to do is we're going to start pumping in radical electrons. So we're going to add in sodium 0. As well as ammonia. So typically when we think of sodium, we think of Na+, like Na+, OH- kind of a deal. Sodium 0 is going to be sodium with an extra electron, so it's neutral, but it really wants to lose this electron so it can have a full octet. So what it'll do is it's going to take that extra electron it has. This is a bit of a radical mechanism, so we're going to be using half arrows. We're going to pump one extra electron into this system here. Change where it is. That's going to split one of our two double bonds from this triple bond to put one electron here, one electron here. Let me go with another color. And because we're breaking down a triple bond, we're going to lose our stereochemistry or our like linear configuration here, and we're going to switch to what a normal double bond would look like. And it's going to want to orient itself like I'll do it the other way. This here. The reason for that is the electrons want to repel each other as much as they can. So we're going to get an electron cloud here and an electron cloud here. If we put it into a cis configuration, they're going to repel each other. So we want them to be facing opposite directions in order to alleviate that. So this will not form. We're only going to get this trans conformation here. From this point, we got ammonia in solution. So we're going to pick up a proton from ammonia. To get this radical here. From this point, we're just going to kind of rinse and repeat. So another sodium 0 can donate an electron to give us a negative charge here. We can pick up another proton from a different ammonia. And this is going to get us to a trans configuration. Get rid of some of this stuff. So summarize reductions. We had an H2. We could fully reduce this down to an alkane here. If we add an H2, oops, with our poisoned catalyst, so Lindlar's catalyst, this is going to stop after a single reduction. Nope. They're going to add H's in a syn fashion, just like they normally would. And then if we add in ammonia and sodium 0, this is going to, nope, not that, give us a trans configuration here. So all three different possibilities gives us pretty much full control over what we want to see from this molecule. And when we start talking about synthesis reactions, there's going to be a lot of using these to kind of manipulate things and go from one to another. All right, let's do some hydrohalogenations. These are really straightforward. We've been talking about them already. They're the exact same reaction as we were doing with a double bond. So we'll talk about these and we'll take a little bit of a break. Double bond, adding in HBr. Allows us to brominate. Triple bond, adding in HBr, so our Br ends up at our more substituted position. The secondary one, our H ended up at our less substituted position. With this alkyne here, gonna have the same thing happen if we add an HBr. Br is going to go to our more substituted position. H is going to go to our less. If we do it a second time, we can dibrominate. Again, it'll follow your normal Markovnikov rules, so both of them will end up on your more substituted position. We can also do this with HCl, HBr and peroxide. This is going to give us our anti-Markovnikov product. If we do this with a triple bond here, so adding an HBr and peroxide. Again, this will still go to our less substituted position. We can do it a second time. One, two, three, four, five. And dibrominate. So these are the same reactions we have been doing. We're just able to do it twice now. That's what I want to do it for. We want to. All right, and then if you have a non-terminal alkyne, it's going to be a bit random. So when you add an HBr, there's two different products that this could form. One's not more likely than the other one. Once you do form this, you get a little bit of a dipole moment, which makes it more likely that your proton is going to get picked up in a second bromination. So if I take one of these over here, at this point, if I throw in, I guess it's just an induction effect. If I throw in more HBr, it's going to selectively put that positive in the same position as the Br was on. So for these reactions, you're always going to get dibromination in the same spot when you're doing these excess ones. We're going to take a little bit of a break. Let's meet back at 10:05, at which point we'll talk about how to make your BRs on opposite carbons. So, yep, let's meet back here at 10:05, take about a 7-minute break. There we go. All right. So we are going to take a look at 9.7, kind of move on to some, did I skip? Jump around. Actually, let's do 9.8 first because that makes more sense. So these are halogenation reactions. If we take our alkyne, well, let's do it with an alkene first. We take our alkene, we throw in Br2. Going to give us anti-addition of 2 bromines here, dibromination. Could do this with an alkyne. Going to do exactly what you expect. It's going to initially dibrominate. And then if we throw it in again, we can tetrabrominate. It's going to give us anti-addition of bromine, so we're going to end up with a trans or an E double bond here. Throwing in Br2 again. Because we have 2 BRs, they're achiral. And we get to our final product. So these brominations are, I mean, they're pretty straightforward. They're doing exactly what they do with the double bonds here. And same thing with these dibrominations, doing exactly what they would do with the double bond. So let's talk a little bit about hydration reactions. So hydration is going to be a little bit different. We think of a hydration reaction with mercury sulfate, or sorry, mercury acetate. Or we can just do it with H plus and H2O. We're going to end up forming an alcohol here. When we do our equivalent reaction with an alkyne, which is going to be fairly similar, we need to add in a mercury sulfate catalyst. But if we take an alkyne, throw in H plus and H2O, which they draw as H2SO4, H2O, and mercury sulfate, we are originally going to get the same thing. From here, what we're going to have happen is what's called an acid catalyzed tautomerization. And what a tautomerization is essentially you're going to pull off a proton from one section and put it on a different one. So we're taking what's referred to as an enol, which is this structure here. We'll talk more about these later in the class. And we are going to move this proton to a different location. So the way that we're going to do that when we're in acid, so we have acid, so H2SO4 and water here are going to form H3O plus. Our double bond can pick up a proton here. At this point, we have two different resonance structures. We either have this or our full octet one. Which would be this here. And at this point, water is going to pull off this proton to give us our final product, which is just going to be a ketone. So looking back at our actual reaction, this is more of a transition state. This reaction will eventually lead us to a ketone. And if we want to compare this to reactions we've been talking about previously, give you guys a second to get caught up on writing. I'll draw this in blue. If you think of like excess HBr, it's going to give us 2 bonds to bromine instead of 1. This reaction is giving us 2 bonds to oxygen instead of 1, but they just happen to be on the same oxygen. So you're forming a double bond to an oxygen instead of like 2 alcohols. So this reaction only really works for a terminal alkyne. Terminal meaning that the alkyne is at the end of the molecule. So for instance, this here, adding in H2SO4 and H2O and mercury sulfate is going to give us a ketone on our more substituted position. So if we think this is primary, this here is secondary, our ketone is going to form on a secondary position. If I do this with a non-terminal alkane, so let's take the same molecule but add a methyl at the end, or ethyl. Let's take this here, add in the same reagent. We've lost that selectivity now. These are both secondary, which means this can lead to 2 products. Got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That seems like too many. 1, 2, 3, 4, 5. Really? Yep. Okay. So we can either have either of these 2 products would be, I guess both of these 2 would be the correct answer for this one. because we have both secondary centers in our alkyne, there's not going to be any sort of selectivity there. Okay, our hydroboration oxidation reaction. Which is our anti-Markovnikov version of this, is going to follow the same principle. So double bond, adding in BH3THF. NaOH and peroxide. Is going to give us our anti-Markovnikov addition. Doing the same thing with a triple bond. In BH3THF. And the book gives a couple of other reagents you can use, but for this class, we're just going to stick with BH3THF. This is going to give us this enol originally, and then we're going to do something similar to what we did before. This is now going to be base catalyzed. Unlike in the first reaction, we were in H2SO4 and water. Now we're in NaOH. So we are going to do a base catalyzed isomerization. Which is going to consist of taking our enol again. We have a base, so this OH minus can pull off a proton. And then we're going to have these electrons come down. We made water. Grab this proton off of our now water to remake our NaOH. And we will effectively shift that H from our OH into this carbon position and allow us to make an aldehyde. So like before, this enol is a transition state that gets us to an aldehyde. Doing the same thing as before, we're making 2 bonds to oxygen. They just happen to be on the same oxygens. This, again, only works in a terminal position. I'll give you guys a minute to get caught up on writing. Okay, so let's take that same example. Throwing in BH3THF. NaOH, peroxide, going to get us to, in this case, our aldehyde. If we have a non-terminal alkyne, so up top we had a primary and a secondary center. In peroxide, we're going to end up adding to this primary center. We're doing an anti-Markovnikov addition. If we have secondary on both sides, it's not going to be selective. It's going to do the same thing as it did with H2SO4, water, and mercury. And we're going to end up with getting two products. From this reaction. So you need to have a terminal alkyne for these reactions to be actually selective. If not, they just add ketones to both positions. And I'll throw in the other one as an example. So this works here, or H2SO4, water, mercury sulfate, HgSO4. I'll put a box around this. These are kind of our three possible reactions you can get with an alkyne for hydrations. Okay, let's look at ozonolysis real quick. Question in the chat is, would there be a hydrogen at the end of that last one, or is it methyl? Yes, so this is a CH3. If I'm counting my carbons over here, there's 1, 2, 3 carbons. So my product 1, 2, 3. This is still a methyl group over here. Just like if I'm counting my carbons up here. 1, 2, 3. So I added, in this reaction, we end up adding 3 or 2 more hydrogens to this position, just like we added them over here to this position. Does that make sense? Okay. Cool. So taking a look at ozonolysis. Again, not going to really go into a mechanism for this one. Our ozonolysis for a double bond. We end up breaking this double bond in half. We end up getting 2 bonds to oxygen from it. If we do this with an alkyne, we're going to get the same thing. We're just going to get 3 bonds to oxygen now. So we were to ozonize this, it changes our reagents a little bit. We got to add in water instead of DMS. Still going to break this triple bond here. In order to get 3 bonds to oxygen, we're going to need to form carboxylic acids. On either side. So very similar concept. We're just making an extra bond to oxygen. Instead of just making aldehydes, we're going to be making all the way down to carboxylic acids. Okay. I don't really want to spend a lot of time on these. I'm going to move on to alkylations, which are a much more useful reaction. So let's talk about these for a little bit. I'll give you guys a second to write this down. All right, so moving on to 9.10, which is alkylations. This is going to be a powerful reaction because up to this point, you guys haven't learned how to make any carbon-carbon bonds. So if we want to do that, and it looks like we'll have a little bit of time to talk through some synthesis today, if we were to take something like this alkyne, which is terminal, we have an H on the end. We can throw in a base. So the one the book really likes to use for this is ammonia, NaNH2. We are going to pull off a proton here and make a good nucleophile. So once we get this negatively charged alkyne, all we have to do is an SN2. So throwing in some sort of haloalkane will let us do an attack on this center here, kick out a bromine. And we are going to elongate our chain. So we added 3 more carbons because that's what we attacked here. This will give us a 1, 2, 3 carbon addition. To make a longer product here. We could potentially do this twice if we had ethyne. So if we were starting with, give you guys a second to get caught up and then I'll erase all this if I have some space. So we take this as a double terminal alkyne. It's literally just 2 carbons here. If we were to throw in our base, so NaNH2, We're going to deprotonate one of these ends. To generate a negative charge here. From this point, throwing in some sort of haloalkane. We can do an SN2 here. To elongate our chain by 3 carbons. So I'm going to kind of abbreviate this up top. So 1, 2, and then from this point, we could do this again. So if we threw in another equivalent of NaOH, or sorry, NaNH2, this is going to let us deprotonate. Let's throw a different haloalkane on there. So we're originally going to make another equivalent. So we'll pull off this proton here. Oops, we're rough. And then we could attack this other haloalkane. And we'll walk through a few of these. And elongate our chain even more. So if I'm counting these out, I'm going to mark this 1, 2, 3 here. Over on our molecule up here, this would be 1, 2, 3. Same thing over here, 1, 2, 3. This would be 1, 2, 3, 4. 1, 2, 3, 4 here. And let's do another one that's not so like chain-like. It's gonna be a little easier to see, I think. So give you guys a few minutes to write this down, then I'm gonna clear it and do a few more of these. All right, so let's take Thine again. This time I'm going to write out all the reagents at the beginning. So we're going to add an NaNH2. Let's put a branch point on this. Another equivalent of NaNH2. Something different here. And walk through this reaction. So our first step is going to be pulling off a proton either end, doesn't matter which side. grab one of these alkyne protons. From here, we can attack this carbon that contains an iodine. We're going to be doing an SN2. Taking that out. And adding 1 carbon, 2, and then our branch point. So if you wanted to number out like 1, 2, 3 here, this would be the same 1, 2, 3 on this carbon. You can also think that this entire alkyne is going to replace this iodine here, if that helps. Get rid of these numbers. Okay. From here, we're kind of rinse and repeating. So adding in another NaNH2. Let's just pull off this proton. We're going to attack this other Br here. And this is going to get us to our final product. So we need the part of the reaction we already had drawn. We can just start up by just redrawing this. Now we've replaced this whole thing, or Br, with this entire thing here. So we need a bond to that carbon, and then a bond to our, oops, too many carbons, cyclohexane here. Any questions on these before I have you guys do one? Okay, I'm gonna draw one of these up, give you guys about maybe 3 or 4 minutes to work through one, and then we'll talk through it together. All right, so I'm gonna check back in at, let's say, 10:44. We will go through this problem and maybe call it for today. Somebody asked where do we find the recordings for the past lectures. At the end of the class, I'll walk through where to go to get them. All right, so let's take a look at this one. For this reaction here, we are going to pull off a proton. And do an SN2 at this position here. We need to add a 1, 2 carbon, so 1, 2, and then this 5-membered ring. Next portion. We are going to pull off another proton, and then this can attack our other side. So we're drawing the original molecule we've had from step 1 and 2. And then we're going to add 1, 2, 3, 4 carbons. So 1, 2, 3, 4 to the end of our chain over here. Okay. So this is the end of the chapter 9 reactions. Do you guys have any questions on these? Tomorrow we'll do some synthesis problems with these and go do a little bit of a review of chapter 10. I don't know how much detail I really want to go into from that chapter in terms of like those mechanisms, but at least cover them a little bit, seeing as they come up a few times from here and there. I am going to quickly share my screen though. Let's see. So someone was asking, how do I get to previous lectures? If you go into your course and you go to modules, there is now something here, which is lecture videos. You click on this, it'll give you a link to Monday's lecture. Today I'll update it and add in today's lecture. So that's how you get to your lectures through the week. Same thing for the recitations. If you go to a recitation, open up a module, there should be a Reci videos file, and same thing. Today for office hours, I'll post a link to it. It's going to be the same link as this Reci to go to your recitations. So, but I'll put something similar on the homepage for Canvas to get there. There was a question. Real quick in the chat. So someone asked, on the homework, they had, what was it? C minus CH3 as a reagent. If you see this as a reagent, treat it like you've already done. Or yeah, I guess. You get a reaction that's like this here, you're essentially doing these a little bit out of order. You're going to do the same thing you were doing before. So this will come in, do an attack, and give you this here. You just kind of switched your reactants and your products. You've essentially condensed from going NaNH2 into writing it in a different form. So this will give you the same product as this down here. Any other questions? If not, I will be in office hours in about 12 minutes, so I'm happy to answer questions there. I'll have a link posted on the Canvas page where you can just go through the RESI link. So I will see you guys tomorrow.